In the summer of 2022, a telescope parked nearly 1,000,000 miles from Earth sent back an image of galaxies that existed when the cosmos was barely 2% of its present age. And those galaxies were massive enough to break the models astronomers had trusted for 40 years. We had assumed the early universe grew up slowly in the dark, taking its time. That assumption was wrong. What the data showed instead was a universe that came alive fast, burned bright, and built structure with an efficiency nobody had physics to explain. Tonight we go through what that telescope actually found. Black holes heavier than the galaxies meant to contain them. Oxygen sitting inside a galaxy born less than 300 million years after the beginning of everything. And a disagreement between two of our most careful measurements of the universe that nobody has been able to resolve. If any of that sounds worth sitting with, stay through to the end, because it only gets stranger from here. On a December morning in 2021, a rocket rose from a launch complex on the coast of French Guiana, carrying the most intricate machine humanity had ever tried to send off this planet. The instrument riding inside weighed a little over 6.5 tons, lighter, in fact, than the space telescope it was meant to replace. That comparison, though, is where the similarities end. This was not a bigger version of an old idea. It was a different kind of eye entirely, built to answer questions the older instrument was never equipped to ask, aimed at a slice of the universe the older instrument could never have reached. Start with the mirror. The primary mirror on the new telescope spans about 6.5 meters, assembled from 18 gold-coated hexagonal segments, each one weighing around 20 kilograms. Its predecessor's mirror measured 2.5 meters across. Surface area, not diameter, is what actually counts here, and by that measure, the new instrument gathers roughly 5 times more light in the same span of time. But the real distinction isn't size. It's the part of the spectrum each instrument was tuned to hear. The older telescope worked in ultraviolet through near-infrared light. This one was built almost entirely for infrared, reaching out to wavelengths nearly 30 times longer than anything a human eye can register. That single design choice is the whole story. There are objects out in the universe that the earlier telescope was physically unable to see, no matter how long it stared. This new instrument was built specifically to find them. Getting it into space at all was, by any honest account, terrifying. To fit inside the rocket's fairing, the entire telescope had to fold. The mirror folded. A secondary mirror on an arm folded, and a 5-layer sun shield roughly the size of a tennis court crumpled down into a package barely larger than a delivery truck. That shield exists for one purpose: to hold the telescope's instruments near 220 degrees below 0 Celsius, cold enough that the telescope's own heat doesn't drown out the whisper-faint infrared signal arriving from the first galaxies. The 3 sources of unwanted heat it had to be shielded from were simple: Earth, the Moon, and our own star. After the rocket did its job, the telescope spent about a month unfolding itself, alone, roughly 1,000,000 miles from home, at a gravitational parking spot where Earth's pull and the Sun's pull cancel out. Engineers had counted 344 individual points in that unfolding sequence where a single mechanical failure would have ended the mission for good. There would be no rescue flight. The older telescope, orbiting just a few hundred miles up, had been visited and repaired by astronauts 5 separate times over its life. This new one was sent somewhere no human hand could ever reach. If any one of those 344 steps had gone wrong, the telescope would simply have sat there, fully built, fully useless, drifting forever. None of them went wrong. Every hinge, every latch, every tensioning cable did exactly what it was designed to do. The mirror segments locked into an alignment more precise than a single wavelength of light. The detectors cooled to their operating temperature. By the middle of 2022, the science began, and within weeks, the people who had spent decades building this thing were saying on the record that it was already outperforming their best-case predictions. The real test was still ahead of it, though. What would happen when this instrument turned its full attention toward the oldest light in existence? Light that had been traveling toward us for nearly 13 billion years, waiting the entire time for something capable of catching it. Here's the physics behind why that ancient light needed a telescope like this one in the first place. As the universe expands, the light traveling through it gets stretched along with the space it's moving through. A photon that left a newborn star as ordinary visible light, emitted by a galaxy assembling itself at the far edge of the observable universe, arrives at Earth billions of years later as infrared radiation. And the farther that light has traveled, the more the expansion has stretched it, and the deeper into the infrared it falls. This isn't a rough approximation. It's a direct, measurable consequence of space itself growing since the light departed. Astronomers call the effect redshift. The older space telescope, staring at the same patch of sky for days at a stretch to build its famous deep field portraits, was picking up galaxies that existed 1 to 3 billion years after the beginning. Past that distance, the light simply fell outside what it could register. But the very first galaxies, the ones that formed once the universe had cooled enough for atoms to exist, were born somewhere between 100 and 400 million years after the beginning. Their light has been in transit ever since, and some of it is landing on Earth's detectors this very moment, carrying information about objects that predate our own solar system by 9 billion years or more. For most of the history of modern astronomy, that light arrived and nobody could see it. No instrument on the ground or in orbit was built to catch it. Ground-based telescopes have an extra problem too. Earth's own atmosphere swallows most infrared wavelengths before they ever reach the surface. The only fix was an instrument cold enough, wide enough, and far enough from the atmosphere to intercept that signal directly. Cosmologists have a name for the era this telescope was purpose-built to observe: the epoch of reionization. It describes the period when the very first stars and galaxies switched on, and their ultraviolet light began burning through the thick fog of neutral hydrogen that had filled all of space since the earliest atoms formed. Before that moment, the universe was essentially opaque. Light couldn't travel far without being absorbed. Then, within roughly the first billion years, the first light sources ignited and cleared the fog, and the universe became transparent for the first time. This telescope was engineered to look straight across that transition and into the darkness on the other side of it, to catch the earliest structures at the exact moment they first switched on. When researchers at an Italian astrophysics institute began combing through the telescope's first deep exposures, they were looking at photons that had departed their sources when the universe was less than 5% of its current age. And what those photons were telling them was already contradicting the standard picture before the telescope's first full year of operation was even finished. The first scientific deep field image from this telescope came out in the summer of 2022. aimed at a massive cluster of galaxies a bit over 5 billion light-years away. That cluster wasn't really the point of interest. It was a tool, a concentration of mass that bends the light traveling around it, a phenomenon called gravitational lensing. Objects far behind the cluster, ordinarily too faint and too distant to register, get magnified and stretched into visibility by the cluster's own gravity, acting like a natural telescope lens layered on top of an artificial one. Combine that trick with a 6.5-meter mirror and detectors sensitive enough to pick up objects 100 times fainter than the older telescope could manage, and the resulting image, covering a patch of sky no bigger than a grain of sand held at arm's length, contained thousands of galaxies. Some were smeared into arcs by the lensing effect. Some glowed deep red, their light stretched by billions of years of travel. Many had never been recorded before. The very oldest among them had emitted their light when the universe was under 1 billion years old. What made the reaction to that image unusual wasn't just its content. It was the fact that this was only a routine calibration image, released to prove the telescope was working. The target had been chosen partly because the older telescope had already photographed the same patch of sky, giving researchers a direct before and after comparison. Galaxies that had taken the older instrument 11 days of exposure to capture as barely visible smudges now appeared with actual structure. Spiral arms, bright cores, color variation suggesting different populations of stars at different ages, captured in a fraction of the exposure time. Researchers were posting side-by-side comparisons publicly within hours. One described the feeling as putting on glasses for the first time and discovering the things you'd only ever theorized about were actually right there in front of you. But buried quietly in that same data was a warning. Several of the galaxies weren't where the leading models expected them to be. Not in brightness, not in size, not in apparent age. And that first image was only a preview. The dedicated survey programs designed to stare at the faintest and oldest patches of sky for hundreds of hours straight hadn't even started yet. One of the most ambitious of those programs set out to systematically map the earliest galaxies in the sky. Led by a team based at the Harvard-Smithsonian Center for Astrophysics, working alongside researchers from the University of Arizona, UC Santa Cruz, and elsewhere. It aimed its cameras at 2 patches of southern sky that the older telescope had already stared at for days, sometimes weeks, to produce the deepest images it was capable of. Overlapping with that old data was deliberate. Every galaxy the earlier telescope had caught became a calibration point, and everything fainter became brand new territory. The scale of the leap is worth sitting with. Where the older telescope needed some 400 orbits and 11 cumulative days of exposure to reach galaxies from roughly 5 to 800 million years after the beginning, appearing only as faint, colorless smudges whose distances had to be estimated rather than measured directly, this new program reached comparable depth in a fraction of the time, and it could do something the older telescope never could. Take actual spectra, precisely measuring distance and chemical composition for hundreds of objects simultaneously. The difference wasn't a modest improvement. It was the difference between knowing a sound came from somewhere down the hall and being able to pick out every individual voice inside the room. The first major spectroscopic results from that survey landed in a scientific journal in early 2023. A team based at a British university confirmed through direct spectroscopic measurement rather than estimation. 4 galaxies existing when the universe was between roughly 300 and 450 million years old. At the time, they were the most distant galaxies ever confirmed this way. And buried in those numbers was something researchers were cautious about stating too loudly at first. These galaxies contained more stars, more total mass locked up in stars than the standard model said should be possible that early. They weren't faint edge of detection smudges. Several were bright and structured, implying stellar populations that had been building for far longer than current theory allowed. A galaxy that far back requires its star formation to have started within the first few 100 million years after the beginning, and the standard model describes that process as gradual. Small pockets of dark matter slowly accumulating enough gas to eventually spark meaningful star formation. The data was telling a different story, and every new confirmed detection pointed the same direction. The reigning framework for how cosmic structure assembles, refined across roughly 4 decades of observation and mathematical modeling, describes a universe that began with tiny quantum fluctuations in density, amplified over hundreds of millions of years by gravity into the first collapsing structures, which pulled in gas that cooled and eventually fragmented into the first stars. It's described as a hierarchical process. Small things form first, and larger structures are built gradually through mergers. This framework has been tested against an enormous range of observations, the afterglow of the Big Bang, the distribution of galaxies nearby, clustering statistics drawn from surveys of millions of objects, and in nearly every one of those tests, it has held up remarkably well. Cosmologists trusted it, but this telescope's first year introduced a genuine problem. Across several independent survey programs, researchers kept finding galaxies at extreme distances that were both brighter and more massive than the model allowed. One large survey out of the University of Texas at Austin cataloged hundreds of candidate galaxies from the first 650 million years of cosmic history, and the excess wasn't subtle. Luminous galaxies from that early era were showing up roughly 10 times more often than predicted. A researcher co-leading one of the widest survey programs, which eventually cataloged around 800,000 galaxies spanning nearly the entire history of the universe, said publicly what a lot of people in the field had been thinking privately. The data kept coming back at odds with the model, consistently, persistently, ever since the telescope first turned on. The uncomfortable question nobody wanted to ask too loudly was whether the model itself was fundamentally broken. There were more conservative possibilities on the table. Maybe stellar mass was being overestimated because light from actively feeding black holes was getting mistaken for starlight. Maybe early galaxies went through unusually intense, compressed bursts of star formation that made them look more massive than their true average history. Both were technically plausible. Neither had strong independent evidence behind it, and both were essentially proposed specifically to save the model from data that otherwise contradicted it. The trouble with those explanations is that they each require the early universe to behave in ways that are themselves completely unexplained. Concentrated star formation intense enough to account for the gap has no known physical mechanism. Widespread misidentification of black hole light for starlight would require enormous numbers of black holes to already exist at absurdly early times, which just relocates the crisis rather than solving it. Every patch applied to the model opened a new seam, and all the seams ran in the same direction. One paper published in early 2023 forced the issue into sharper focus. A team based at an Australian university, analyzing data from that early survey, identified 6 galaxies formed within the first 5 to 700 million years after the beginning, each estimated to hold somewhere between 10 billion and 100 billion solar masses worth of stars. For comparison, our own galaxy, a moderately large one by present-day standards, contains roughly 60 billion solar masses in stars, built up over more than 13 billion years. These 6 objects reached comparable mass in under 5% of that time. The issue wasn't the observation itself. It was what the observation demanded be true. Under the standard model, galaxy formation starts with regions of slightly denser dark matter that grow by pulling in gas, which cools and eventually ignites into stars, and the rate at which any known process can convert raw gas into stars is physically constrained. Typical galaxies across cosmic history convert somewhere between 5 and 10% of their available gas into stars over their entire lifetimes. To build up that much stellar mass in under 500 million years starting from nothing, these galaxies would have needed to convert nearly all of their available gas into stars continuously from the very beginning, without pause. That kind of efficiency isn't just unusual. Under everything we know about star formation and the way young stars and black holes heat and expel surrounding gas, it borders on physically impossible. One cosmologist at UT Austin who had spent years building theoretical predictions for early galaxy populations described the tension bluntly, in the kind of precise statistical language that in this field signals a genuine crisis rather than a minor calibration issue. Another researcher at the University of Colorado Boulder called the objects absolutely wild, saying they implied either an early universe more chaotic and efficient than anything modeled before, or physical rules governing star formation that simply hadn't been identified yet. Later follow-up work added some nuance. A portion of the apparent stellar mass in some of these candidates turned out to come from actively feeding black holes rather than actual stars, meaning some of the original mass estimates had been inflated. Other researchers proposed that unusually intense, short bursts of star formation could explain part of the excess. These corrections shrank the size of the crisis. They didn't erase it. Even after adjustment, the population of massive early galaxies remained roughly 10 times more common than the standard model predicted. Informally, researchers started calling these objects the universe breakers, and the nickname turned out to be more literal than most nicknames earn the right to be. In the spring of 2024, an international team confirmed the most distant galaxy ever directly measured through spectroscopy, an object whose light left it when the universe was just 290 million years old, roughly 2% of its current age, predating our solar system by more than 9 billion years. This wasn't a faint smudge sitting right at the edge of detection. It measured over 1,600 light-years across and contained hundreds of millions of solar masses in stars. One of the researchers noted the team could have picked this galaxy out even if it had been 10 times fainter, meaning objects like it, or larger, could plausibly exist even deeper in time, perhaps within the first 200 million years after the beginning. The confirmation alone would have been remarkable. Then came the follow-up. In early 2025, combined data from the Space Telescope and a large radio observatory in Chile picked up a very specific chemical signature inside that same galaxy, oxygen. And the presence of oxygen anywhere in the early universe carries an implication that can't be waved away. Oxygen isn't primordial. The beginning of the universe produced almost entirely hydrogen and helium, with only trace amounts of anything heavier. Every atom of oxygen anywhere in existence was forged inside a star and released only when that star died, either by shedding its outer layers gently at the end of its life or by detonating as a supernova. For oxygen to show up in a galaxy, that galaxy has to have already hosted at least one full generation of stars that lived out their entire lifespans and died. The timeline this demands is staggering. The massive stars capable of exploding and seeding their surroundings with oxygen typically live only a few million to a few tens of millions of years. But before those stars could even exist, an earlier generation had to form, live and die first, enriching the surrounding gas enough for the next generation to inherit heavier elements. All of that, first ignition, multiple stellar generations, chemical enrichment, and full galaxy assembly, had to happen inside the first 290 million years. Under the models that existed before this discovery, that period was barely passed when the very first stars were even expected to begin forming in the first place. One researcher on the team called the finding completely unanticipated, and the phrase understates just how much revision it demands. A separate and equally strange crisis was building in parallel, this time around black holes. Supermassive black holes, ranging from millions to billions of times the mass of the Sun, sit at the centers of most large galaxies in the present-day universe, including our own. The one at the heart of the Milky Way weighs in at around 4 million solar masses. Their existence is so routine that astronomers factor a central black hole into nearly every model of how a large galaxy behaves. The problem this telescope introduced was one of timing. Growing a black hole from a stellar-sized seed up to supermassive scale takes time, governed by a hard physical ceiling on how fast matter can fall in before the radiation pressure it generates blows the surrounding fuel away. Even at that theoretical maximum growth rate, assembling a black hole of 100 million to a billion solar masses takes hundreds of millions of years under close to ideal conditions. And yet the telescope kept finding them earlier than that math allows. One confirmed detection placed a black hole of around 1.6 million solar masses at a galaxy existing roughly 400 million years after the beginning, actively feeding at a rate of about 1 solar mass every 5 years. Another, using combined X-ray and infrared data, found a black hole of 10 to 100 million solar masses at around 450 million years. The deeper crisis, though, came from an entirely new class of objects that researchers began cataloging in large numbers and gave the informal nickname little red dots. They're compact, red, and structured in a distinctive way in their light output. Their central black holes range from 1 million to 100 million solar masses. And here's the part that broke the model. In the present-day universe, a galaxy's central black hole typically accounts for around 1/10 of 1% of its total stellar mass. In these little red dots, that ratio ran to 30% or higher, roughly 300 times the locally observed relationship. These black holes weren't just slightly ahead of schedule. They appeared to dominate their host galaxies in a way current theoretical frameworks have no accepted mechanism to produce. Researchers studying them said plainly that the data was real. The interpretation was the problem. A few candidate explanations were floated. One invoked direct collapse, the idea that under very specific early universe conditions, a massive cloud of primordial gas could collapse straight into a black hole without ever passing through a stellar phase, giving it a head start of tens of thousands of solar masses right out of the gate. Plausible in principle, but producing hundreds of these objects in the numbers actually observed stretches the mechanism thin. A second explanation required sustained growth faster than the theoretical speed limit for hundreds of millions of years straight. Technically possible in brief bursts under simulation, but the energy output at that rate should have destroyed the surrounding galaxy. And yet these systems show evidence of ongoing star formation happening at the same time. A third, less popular but harder to dismiss outright, invoked primordial black holes, objects theorized to have formed directly from density fluctuations within the first second after the beginning, long before any star existed, and long proposed as a possible partial explanation for dark matter itself. None of the three explanations has achieved consensus. What's clear is that these little red dots showed up 10 to 100 times more often than expected, each one outweighing its own galaxy by a ratio seen nowhere else in the nearby universe, and the people studying them have said, with as much precision as scientific language allows, that they cannot yet explain what they're looking at. By the end of 2024, roughly 2.5 years into operation, a pattern had emerged that no single result had fully revealed on its own. Across multiple independent survey programs pointed at different patches of sky, at different wavelengths, led by different teams, the findings kept pointing the same direction. The early universe, roughly the first 100 to 700 million years, wasn't the slow, gradual dawn the standard model described. It was faster, denser, more chaotic, and far more chemically productive than any framework built before this telescope had anticipated. Stack the constraints together. A galaxy with fully formed oxygen at 290 million years, meaning multiple stellar generations had already lived and died. Galaxies with Milky Way scale stellar mass at 500 to 700 million years, meaning star formation efficiency approaching 100% from the very start. Black holes with masses 30% or more of their host galaxy's total stellar mass, at rates 10 to 100 times more common than predicted. Each of these findings on its own was a serious problem. Together, they suggested something much bigger. The word that kept surfacing across papers and conference talks through 2024 and 2025 was efficiency. The early universe appeared to convert gas into stars, assemble galaxies, and grow black holes at rates that violate the established physics of every one of those processes individually. 3 broad explanations have been proposed, none with a decisive edge. Maybe early star formation was simply more efficient, denser gas, different turbulence. conditions that let more of it collapse into stars before feedback processes could shut things down. Maybe the standard picture of dark matter is incomplete, and a different candidate would naturally produce a different, faster pattern of early structure formation. Or maybe, the most uncomfortable option, there's an error somewhere in the cosmological model's treatment of the very earliest moments, possibly in the rapid inflationary expansion phase that set the initial conditions everything else builds on. None of the three has consensus support. All three remain under active investigation. What isn't in dispute anymore is the character of the discrepancy. The universe didn't assemble itself slowly and patiently. In its first several 100 million years, it did something that from our current distance in time looks almost instantaneous. A burst of structure, chemistry, and mass governed by physics the field hasn't fully identified yet. At efficiencies the field didn't think were possible. This telescope wasn't built only to look backward in time. It was also built to see the vast structural scaffolding of the universe at its largest scales, the parts the earlier telescope's instruments simply missed. When its infrared detectors began mapping how galaxies are distributed across hundreds of millions of light years, what emerged was something theorists had predicted in rough outline for decades, but had never actually seen with this level of clarity. A three-dimensional web of matter stretching across the entire observable universe, organized into filaments, sheets, dense nodes, and enormous empty voids, on a scale no everyday comparison really captures. This cosmic web is the largest coherent structure that exists. It formed because the early universe wasn't perfectly smooth. Tiny variations in density, imprinted during the earliest fraction of a second, got amplified by gravity over hundreds of millions of years. Matter fell along invisible channels defined by dark matter, piling up where those channels intersected into dense clusters, while the space in between was slowly emptied out. In two-dimensional maps of survey data, it looks almost like a foam. Bright, interconnected strands with dense nodes where they meet, and vast dark gaps in between. Galaxies crowd the filaments and nodes. The voids between them are nearly barren. A typical filament connecting two galaxy clusters can stretch 100 to 300 million light years and contain more mass than thousands of individual galaxies, most of it invisible dark matter, mapped not by direct imaging but by how it gravitationally organizes the visible matter around it, how it bends background light, and how galaxies statistically cluster along its path. One researcher at the University of Hawaii, whose team tracked the velocities of tens of thousands of galaxies to trace this flow, described the result as a system of cosmic watersheds. Just as rivers flow downhill toward the sea, galaxies flow along channels defined by the dark matter web toward the densest concentrations of mass, which function as the ocean basins of the cosmos. What this telescope added to that picture was depth. Earlier surveys had mapped the web relatively nearby. This telescope let researchers trace that same architecture much further back in time, to periods when the web itself was younger and denser, measuring the positions and velocities of galaxies along filaments that had already formed within the first 2 billion years of cosmic history. What they found was that the web's basic architecture, clusters connected by defined filaments, was already in place earlier than the models predicted. At epochs when structure formation, according to the standard picture, should still have been in its infancy. The consequence isn't abstract. These filaments connect everything. Every galaxy cluster sits embedded in a network of dark matter channels, linking it to its neighbors, near and far, with matter flowing continuously along those channels toward regions of higher density. Individual galaxies aren't isolated islands drifting through empty space. They're threaded into a web that shapes their trajectories, their gas supply, their star formation, and ultimately their fate. Our own galaxy sits inside this web. Its path through space, its eventual collision with its nearest large neighbor, the structure of the small cluster of galaxies it belongs to. All of it is shaped by dark matter filaments running through our cosmic neighborhood. And it turns out the web also contains regions of a very different character from the filaments where galaxies actually live. The very existence of a cosmic web implies, as a structural necessity, that the web has gaps, enormous ones, regions where filaments simply never formed, where matter migrated outward over billions of years toward the surrounding structure, leaving behind an emptiness so extreme it doesn't map onto any everyday human experience of space. These are called voids. The largest confirmed example sits in the direction of a northern constellation, and the numbers describing it are worth sitting with. It measures roughly 330 million light-years across at its widest point. It was discovered in 1981 by a team at Harvard doing a systematic survey of galaxy distances, expecting to find some variation across their survey volume. Filaments here, relative emptiness there. Instead, they found a roughly spherical region containing almost nothing. In a universe where typical galaxy separation within clusters is measured in mere millions of light-years, this 330 million light-year sphere contained around 60 galaxies, where the models predicted thousands. The lead researcher reportedly said afterward that the void was so large he was embarrassed to report it. It's vast enough that the entire filamentary cosmic web described a moment ago could be nested inside it with room to spare. It's old enough that nearly every galaxy that might once have populated its interior has migrated outward over the age of the universe, pulled by the gravity of everything surrounding it, leaving behind a handful of galaxies clustered near its center, rather than any meaningful distributed population. Here's the specific consequence of that scale that's worth pausing on. If our own solar system sat at the exact center of that void, in the same location it currently occupies relative to everything around it, astronomers here wouldn't have confirmed the existence of other galaxies until the 1960s. The nearest external galaxies would have sat so far beyond the reach of 1920s era instruments that the entire conceptual revolution of recognizing just how vast the universe actually is would have been delayed by decades. We'd have lived as an astronomical civilization inside a vast, near-total emptiness with no visible evidence through early century instruments that any other galaxy existed at all. What makes this void unsettling in a way that extends past its raw dimensions is what it demonstrates. The universe's distribution of matter is so uneven that your specific location within it determines your entire picture of reality. The observable universe, as seen from deep inside a void, and the observable universe as seen from inside a dense filament, are empirically different places, even if the underlying physics governing both is identical. And that raises an uncomfortable possibility. maybe our own cosmic neighborhood isn't the dense, typical region we've quietly been assuming it to be. That particular void is an extreme case, but researchers examining the region surrounding our own position have gradually assembled evidence for something less dramatic, but potentially far more consequential: the possibility that we ourselves live inside a void. This one, characterized systematically in a 2013 paper, describes an underdense region roughly 2 billion light-years across, centered close to our own local group of galaxies, where the average density of matter runs substantially below the cosmic mean. 2 billion light-years needs framing. The extreme void described above measures 330 million light-years across. This one is 6 times larger in diameter. It encompasses the vast supercluster our own galaxy belongs to, a distant concentration of mass that much of our local universe appears to be gravitationally flowing toward, and hundreds of millions of light-years of surrounding space in every direction. Our own small cluster of galaxies sits well within its interior, not at some extreme edge, but roughly inside a structure whose boundaries have now been traced through the positions of thousands of galaxies across multiple independent surveys. This matters for reasons well beyond geography, because it connects directly to a crisis that's occupied cosmologists for nearly a decade: the disagreement over how fast the universe is currently expanding. The two most precise methods for measuring that expansion rate produce answers that disagree at a level of statistical confidence that, under normal circumstances, shouldn't be possible if both methods are correct. One method works from the earliest light in the universe, using patterns baked into the cosmic microwave background to infer an expansion rate. The other works from a chain of calibrated distance measurements running from our own galactic neighborhood out to increasingly distant galaxies, measuring the expansion directly. The early universe method lands around 67 kilometers per second per megaparsec. The direct local measurement lands around 73. Expressed in the statistical language physicists use to judge these things, the gap sits at 5 to 6 standard deviations, well past the threshold particle physicists use to declare something a confirmed discovery rather than a coincidence. The connection to that local void is specific and unresolved. A region of lower than average density behaves differently under gravity than the cosmic average. Galaxies inside a void tend to get pulled outward toward its walls as the void empties over time, adding extra outward motion on top of the universe's overall expansion. If our position inside that underdense region is adding a systematic boost to the measured velocities of nearby galaxies, then local expansion measurements could be reading artificially high, not because any single measurement is wrong in some simple technical sense, but because the local measurement and the early universe calculation may genuinely be measuring two different things. We could be measuring the universe from inside a bubble, and the bubble could be teaching us a distorted number. Whether this fully accounts for the discrepancy remains contested. Some analyses find the underdensity isn't quite pronounced enough to explain the full gap. Others find that once its influence is properly modeled, the tension shrinks toward levels that might reflect remaining measurement error. What's clear is that our specific address within the universe's large-scale structure isn't a neutral fact. It carries measurable consequences for what our instruments tell us about some of the most fundamental numbers in cosmology. The void we live inside has a boundary, and beyond its edges, matter has accumulated into the structures gravity has spent billions of years assembling. The nearest and largest of those structures, the one containing our own galaxy and roughly 100,000 of its galactic neighbors, was only formally identified and named in 2014 by a team at the University of Hawaii who mapped it using a technique quite different from a normal galaxy survey. Rather than mapping where galaxies sit, they mapped where galaxies are moving, using a catalog of tens of thousands of individual galaxy velocities to reconstruct the underlying gravitational landscape producing that motion. Galaxies don't sit still relative to their neighbors. They move, and the direction and speed of that motion traces the mass distribution around them, even in places where no visible matter exists. Following that velocity field outward in every direction from our position revealed the boundaries of the gravitational basin our own small galactic cluster belongs to, a supercluster roughly 500 million light-years across, containing over 100,000 galaxies and a total mass, stars and dark matter combined, equivalent to something like 100 million billion solar masses. Our own galaxy sits near its outer edge. The nearest large cluster of galaxies to us sits near its center. And the entire supercluster is flowing slowly inward toward a region in a particular direction that the researchers identified as the primary point of attraction. Everything inside this structure is drifting toward that central concentration, pulled by gravity that's been accumulating mass since the early universe. The fact that a structure this large went unmapped as a single coherent object until 2014 says something about how difficult the very largest scales of the universe are to perceive. Individual galaxies are visible objects. Clusters of galaxies had been cataloged for decades. But a supercluster 500 million light-years across, defined by velocity fields rather than any visible boundary, requires a very specific kind of measurement at a very specific scale to even recognize as a single thing. A later update using an expanded catalog of galaxy distance measurements, published in 2023, confirmed the structure while also revealing something else: superclusters across the local universe. On average, run about an order of magnitude larger than the standard cosmological model predicts they should. And this particular supercluster is itself already flowing towards something else entirely. That something else has its own name and its own observational headache. The entire supercluster, all 500 million light-years of it, all 100,000 galaxies, is drifting at roughly 600 kilometers per second toward a concentration of mass in a specific direction, one that happens to sit almost exactly behind the flat disk of our own galaxy as seen from Earth. Dust and gas in our galaxy's disk absorb and scatter most forms of light passing through that direction, creating what astronomers call a zone of avoidance, a band across the sky that ordinary surveys simply cannot see through clearly. X-ray and radio observations can partially cut through it, and dedicated surveys have mapped portions of the dense galaxy cluster sitting near the center of that hidden region. But the full extent of the mass responsible for this pull remained hard to characterize directly for decades, precisely because the tool best suited to mapping it, optical distance surveys, was exactly what the dust cloud blocked. What lies beyond that hidden attractor, visible to surveys approaching from the sides of the obscured zone, is an even larger structure, the densest known concentration of galaxies in the local universe, roughly 650 million light-years from our position. First noticed in the 1930s by a Harvard astronomer studying the scale of the universe, though its true extent wasn't understood until much later. Modern surveys describe it as containing mass equivalent to roughly 8,000 typical galaxies, organized into dozens of clusters linked by dense filaments, with a total volume about 10 times larger than our own supercluster. The velocity measurements across our local universe suggest many of the galaxies in our region are ultimately being drawn not just toward the nearer hidden attractor, but past it, toward this much larger concentration, a gravitational sink that's been accumulating mass for billions of years and whose influence stretches across a meaningful fraction of the observable universe. This picture, superclusters flowing toward attractors, attractors sitting inside even larger gravitational basins, basins draining toward even bigger concentrations, repeats at successively larger scales until it runs into the cosmic web itself, where the filaments carrying matter toward clusters thin out, and the voids separating them take over as the dominant feature. Every galaxy in this picture belongs to some basin of attraction defining where it's ultimately headed, the way every drop of water belongs to some watershed defining which ocean it's flowing toward. And the measured velocities behind all of this, the actual speed at which galaxies are moving through this landscape, eventually produced a number that flatly refused to agree with the number derived from the oldest light in the universe. That disagreement, growing more precise and more stubborn with every year of new data, is now the single most serious open crisis in cosmology. In 2011, 3 researchers working independently were awarded the Nobel Prize in Physics for discovering, back in 1998, that the universe's expansion isn't just continuing, it's accelerating. That discovery, made through careful measurements of a particular class of exploding star at varying distances, introduced the concept of dark energy as the dominant component of the universe, a mysterious force pushing galaxies apart at an ever-increasing rate. Winning that prize required knowing precisely how fast the universe was expanding, expressed as a single number now called the Hubble constant, and pinning that number down with precision became one of the central goals of observational cosmology for the following decade. One team refined the local direct measurement throughout the 2010s, using a chain of calibrated distances, starting with parallax measurements of nearby stars, moving to pulsating variable stars in nearby galaxies, and finally to distant exploding stars bright enough to be seen across billions of light years, each rung of the ladder calibrated against the one below it, stretching from our own galactic backyard out to distances where the universe's pure expansion dominates over local gravitational motion. By 2022, that team had measured the Hubble constant at just over 73 kilometers per second per megaparsec. The other value, derived from the cosmic microwave background and published with the highest available precision in 2020, sits at just over 67%. Both measurements are extremely precise. They disagree by roughly 6 kilometers per second per megaparsec at a statistical significance of 5 to 6 sigma. For years, the hope was that this gap would dissolve once every source of measurement error had been fully accounted for. That hope got directly tested once this new telescope, with its superior sensitivity and resolution, began reobserving the exact same variable stars and exploding stars in the exact same galaxies the earlier measurements had relied on. The results, published in 2023, confirmed the earlier numbers with high precision. The locally measured expansion rate came out to roughly 72.6%, matching the previous measurement of 72.8% almost exactly. Instrumental error had been one of the most plausible explanations for the discrepancy, and this new, far more capable telescope had effectively ruled it out. As the lead researcher put it, once measurement error was taken off the table, what remains is the real possibility that we have misunderstood something fundamental about the universe. A separate, independent team at the University of Chicago, using different distance indicators entirely, found that 2 of their 3 methods landed closer to the early universe value, while 1 matched the higher local value, concluding that a systematic error likely remained in one of the approaches. The team behind the original, more established method maintains their measurement is real, refined over more than a decade, and checked by multiple independent groups. The field, as of now, has no consensus. What it has instead, confirmed by the most precise telescope ever built, is a genuine, unresolved crisis sitting at the foundation of cosmology. In the spring of 2024, a major spectroscopic survey using a ground-based instrument in Arizona released results from its first year of operation. The most detailed three-dimensional map of large-scale cosmic structure ever assembled, built from the measured distances of more than 6 million galaxies. Its purpose was to test whether dark energy, the force driving the universe's accelerating expansion, behaves the way the simplest models say it should. The simplest model treats dark energy as a true constant, a fixed property of empty space itself, unchanging across all of cosmic history, first introduced by Einstein in 1917, later discarded, then revived once accelerating expansion was actually discovered. This survey's data, combined with measurements from other major projects, told a different story. The combined analysis found a deviation from that constant value model at a statistical significance approaching 4 sigma, suggesting dark energy's behavior has actually changed over cosmic time. A separate analysis published later in 2025 found that dark energy appeared to have weakened by roughly 10% over recent cosmic history, at a confidence level above 99%. This result is extraordinary given what dark energy represents. It makes up roughly 68% of all the energy that exists. Ordinary matter, everything ever seen, touched, measured, or modeled across the entire history of science, makes up only about 5%. If dark energy can change, if the force determining the ultimate fate of the universe has been evolving throughout cosmic history, then every prediction that assumed it stays constant needs to be revisited. The future of everything, whether expansion continues forever, accelerates without limit, or eventually reverses, becomes genuinely uncertain in a way it wasn't before this data came in. The simplest alternative to a fixed cosmological constant is a hypothetical field permeating all of space that slowly evolves over time, growing weaker or stronger as the universe ages. Unlike a pure constant, which has no underlying physical mechanism and is simply inserted into the equations as a measured number, this kind of evolving field arises naturally from certain extensions of particle physics. The challenge is that matching the newest data requires this field's evolution to be extremely slow and finely tuned, behaving as though essentially constant for the first 10 billion years of cosmic history, then shifting measurably only in the last few billion. Why a genuinely dynamic field would sit still for most of time and only recently start changing is a question none of the current frameworks answer convincingly. There's something even stranger buried in the details, though. Something specific to how physicists describe dark energy's behavior mathematically, using a parameter that essentially measures how its pressure relates to its density. For a true constant, that parameter sits at exactly -1. Values above that describe dark energy weakening over time, potentially letting gravity eventually reverse the expansion. Values below -1 describe something with its own name in the literature: phantom energy, which grows stronger as the universe expands. The more space that exists, the more energy it contains, and the faster it pushes everything apart, without limit, eventually overwhelming every other force in nature. Researchers at a UK university, analyzing this new survey data alongside other measurements, found evidence for something the simplest theoretical models specifically forbid: dark energy whose behavior crossed that boundary, appearing to have acted as phantom energy in the past, before weakening back above the threshold in more recent cosmic history. That crossing is theoretically awkward because the simplest models, including a plane constant, physically cannot cross that line. They sit on one side and stay there permanently. The data appeared to describe a universe where dark energy had done something its own simplest description says is impossible. As one researcher on the project put it plainly, dark energy seems to have behaved as phantom energy in the past, but isn't phantom now. And the simplest theories simply don't allow for that kind of behavior. The implication is that dark energy isn't some fixed, unchanging property baked permanently into space. It's dynamic, evolving, its influence on the universe shifting across time in ways not yet understood. For decades, the standard picture had the universe's future written out clearly. Endless accelerating expansion until every galaxy beyond our own small cluster crosses beyond any possible observation, and the universe cools into darkness over almost incomprehensible timescales. That picture required dark energy to hold steady. This new data has introduced serious doubt about whether it does. And the phantom phase, if it's real, carries its own genuinely terrifying implication. A universe where dark energy behaves as phantom energy doesn't simply expand forever. It expands at a rate that keeps accelerating without bound, and eventually the structure's gravity holds together. Galaxy clusters, individual galaxies, star systems, eventually planets, eventually atoms themselves, get progressively torn apart as the outward force overwhelms whatever is holding them together. This scenario has a name: the Big Rip. On its timeline, roughly 2 billion years before the end, the gravitational bonds holding galaxy clusters together give way. 60 million years before the end, our own galaxy is torn apart. 3 months before the end, our planetary system is dismembered. 30 minutes before the end, Earth itself is pulled apart. In the final fraction of a second, individual atoms are ripped apart by the same force. Current data doesn't confirm this future is actually coming. The evidence suggests dark energy was phantom in the past and has since weakened. But the fact that it apparently crossed that line at all, that it behaved for some stretch of cosmic history according to physics the standard model doesn't allow, means we can't simply read the future off models that assumed it never would. There's a third possible ending, revived in a 2025 paper from a researcher at Cornell. That analysis focused on the cosmological constant itself, proposing that rather than being a fixed positive value driving eternal expansion, it might actually be a temporary metastable state. The current universe occupying one particular energy configuration out of a broader landscape of possible ones, slowly evolving away from it. If the deepest underlying value is actually negative, the current phase of accelerating expansion is temporary, and gravity eventually wins. The specific timeline this model produces, the universe is currently around 13.8 billion years old. Total lifespan comes out to roughly 33 billion years. The current accelerating expansion continues for roughly 11 more billion years before gravity reverses it. From there, a slow contraction begins, gradually accelerating, until everything collapses back into a single point, what cosmologists call the Big Crunch, arriving roughly 20 billion years from now. For context, our own star has about 5 billion years of fuel left. Our solar system would survive into the contracting phase, witness the expansion slow and reverse, and eventually be crushed along with everything else. Independent researchers analyzing supernova data in 2025 found separate evidence the universe may have already entered a phase of decelerating expansion, consistent with a weakening cosmological constant rather than a steady one. This scenario had actually been the dominant one in cosmology for most of the 20th century, before the 1998 discovery of accelerating expansion seemed to rule it out entirely. This new data reopened the question. None of it confirms the Big Crunch outright. It confirms that the matter is genuinely unsettled again, after roughly 30 years of assumed consensus dissolved in about 2 years of new, more precise measurement. What makes the collapse scenario specifically unsettling is the timeline set against familiar milestones. The contraction wouldn't begin dramatically, it would start as a barely perceptible slowing in the expansion rate, easy to miss against the ordinary background motion of galaxies. Over time, galaxies drifting apart for billions of years would slow, stop, and eventually begin drifting back together across timescales comparable to the current age of the universe. The faint afterglow of the Big Bang, cooled today to just a few degrees above absolute zero and spread evenly through space, would begin heating up again as the shrinking universe concentrated that energy back together. In the final stages, temperatures would climb high enough to dissolve galaxy clusters, then stars, then atoms themselves, collapsing everything that ever existed into a single point. So there are 3 possible endings sitting on the table right now, with roughly equal scientific standing. A long, cold fade into maximum entropy on time scales measured in numbers with dozens of zeros. A violent accelerating dismemberment of every bound structure in existence, or a crushing collapse back into a singularity on a timescale the universe is, relatively speaking, already old enough to be closing in on. Each is total. Each operates on a scale that overwhelms any ordinary human sense of consequence. and each is governed by forces we're now discovering are neither fully understood nor, apparently, fully stable. Step back far enough from any single discovery in this story, and one picture assembles itself. The universe operates on forces at scales and timescales that human civilization has had the tools to measure for barely a few decades. And those forces aren't as stable as earlier generations of physicists assumed. Gravity is the oldest character in this story. It shaped dark matter into the cosmic web, pulled the first gas clouds into the first stars, assembled galaxies into clusters and superclusters, and drives the flows pulling our own local universe toward those distant, hidden concentrations of mass. On the smallest scale, it's the same force holding Earth in orbit and the atmosphere against the ground. On every scale simultaneously, gravity organizes, builds, and, given enough time and density, eventually destroys. Dark energy is the counterforce. It makes up 68% of everything that exists, and yet it has no physical description beyond a term inserted into an equation. Its origin is unknown. Whether it's a fixed property of space or an evolving field is now actively contested by the best data available. It has already apparently behaved in ways its simplest description says it can't, crossing the theoretical boundary at some point in the past. Its current trajectory, strengthening, weakening, or holding steady, determines whether the universe ends in cold entropy, violent rupture, or total collapse. 68% of everything, and we don't actually know what it is. The disagreement in expansion rate sits between these two forces, refusing to resolve. Two extremely precise measurements of a single number, made through entirely different physical methods, drawing on entirely different portions of cosmic history, producing answers that disagree at 5 to 6 standard deviations. The most capable telescope ever built confirmed the disagreement is real, not some artifact of instrument error, and that neither measurement can simply be wrong in a straightforward, fixable way. Either our model of the early universe is incomplete, or our model of the local universe is, and we currently exist inside that unresolved conflict, reading it with instruments that have only been operating for a handful of years. That underlying character, chaos, collision, and violence rather than gradual peaceful growth, shows up in far smaller stories too, down to the trajectories of individual stars. In 2019, an astronomer analyzing data from a large spectroscopic stellar survey found something that didn't fit. A star roughly 29,000 light-years away, moving at about 6 million kilometers per hour, roughly 10 times the typical speed of a star in our galaxy's disk, and about 0.5% of the speed of light. For comparison, the fastest human-made object ever launched, a solar probe, tops out at around 700,000 kilometers per hour at its closest approach to the Sun. This star was moving 8 times faster than that. The research team reconstructed the star's path backward through models of the galaxy's gravity and found it had originated near the very center of the Milky Way in the dense stellar environment surrounding our galaxy's own central black hole, and had been launched outward roughly 5 million years ago, long before modern humans existed. The mechanism responsible has a name first proposed theoretically back in 1988. If a pair of stars orbiting each other passes close enough to a supermassive black hole, the black hole's tidal forces can rip the pair apart, capturing one star into a tight orbit while flinging the other outward at extreme velocity, carrying away the orbital energy of the original pair, amplified enormously by the black hole's gravity. That's exactly what this star appears to be, and its trajectory carries it not to some other part of the galaxy, but entirely out of it. It's unbound. The galaxy's gravity isn't strong enough to ever pull it back. It will keep accelerating outward past the edge of the stellar population into the vast emptiness between galaxies, where it will drift for billions of years before its fuel finally runs out and it dies alone as a cooling white dwarf with no other star within millions of light years. The lead researcher on the broader survey that caught this object described it as a visitor from a strange land. A colleague summarized its life story more precisely. Born near a supermassive black hole, surrounded by countless stellar neighbors, it will leave the galaxy entirely and die completely alone in the middle of nowhere. That contrast, dense, violent origin, isolated, permanent exile, is a fairly accurate summary of what the universe tends to do with its objects generally. It builds them in extraordinarily dense, violent environments, then scatters them across distances so vast that any further connection to their point of origin becomes physically impossible. And this specific discovery confirms something bigger about our own galactic center. The black hole at the heart of the Milky Way has been flinging stars outward at escape velocity for billions of years. A small fraction of our galaxy's stellar population has always, quietly, been in the process of leaving. The galaxy we experience as a stable, permanent home is simultaneously a machine that continuously ejects some of its own members into permanent isolation. If a single star can be ejected by the forces at our galaxy's center, an entire solar system can eventually be ejected by forces operating on a much larger scale. Our nearest large neighboring galaxy currently sits about 2.5 million light-years away, closing the distance at roughly 110 kilometers per second. A measurement confirmed independently through multiple different methods. In roughly 4.5 billion years, the two galaxies will begin their first gravitational interaction. Within roughly 6 billion years, they'll have merged into a single new galaxy. Every star system in both galaxies will experience this event in some form. Understanding what a galaxy collision actually involves requires letting go of the word's usual meaning. Galaxies are mostly empty space. The average distance between stars in our own galaxy is about 4 light-years. When two galaxies merge, the odds of any individual star physically striking another are essentially zero. What happens instead is an interpenetration. Two enormous gravitational fields overlapping, deforming each other's structure, generating tidal forces across hundreds of thousands of light years, and gradually reshuffling their combined stellar populations into new orbits over hundreds of millions of years. Gas clouds collide and compress, triggering intense bursts of new star formation. The supermassive black holes at each galaxy's center spiral toward one another and eventually merge, releasing gravitational waves detectable across cosmic distances. The two galaxies as distinct, recognizable structures cease to exist, replaced by something new. For any individual star system caught up in this, including potentially our own, the merger reshapes the entire local gravitational landscape. Simulations from researchers at Harvard found that roughly 12% of the star systems currently in our galaxy will be ejected into intergalactic space sometime during this merger process, the same mechanism that flung that hypervelocity star outward, operating now at galactic scale. 12% isn't a small number. It represents billions of individual star systems sent permanently into the void between galaxies. Recent observations of our approaching neighbor's outer stellar halo have added more detail to an already violent history. That halo shows clear evidence of multiple past mergers and absorbed smaller galaxies, each event leaving behind trails of disrupted stars visible in its structure today. The galaxy heading toward us has been considerably more active than previously understood, and some updated simulations now suggest the first gravitational interaction might begin as early as 3.5 billion years from now, rather than 4.5. And this looming collision is really only the latest chapter in a process that's been ongoing throughout both galaxies' histories. Our own galaxy shows clear evidence of a major past merger, absorbed somewhere between 1 and 3 billion years ago, in which we pulled in a galaxy roughly a quarter our current mass. The chemical and orbital fingerprints of that ancient event are still embedded in the populations of stars in our galactic halo today, readable by modern instruments like a geological record of past violence. What this telescope has revealed is that galaxy collisions aren't rare exceptions. They're the actual mechanism by which galaxies grow. And in the early universe, that mechanism was operating at a pace that makes our current era look remarkably calm by comparison. In early 2026, a team based at Texas A&M announced the detection of 5 separate galaxies caught in the act of merging, at a point roughly 800 million years after the beginning. The observation required some of this telescope's deepest exposures yet, targeting a region where spectroscopic data confirmed all 5 objects belonged to the same cosmic epoch. 5 distinct galaxies with overlapping structures, deformed halos, and clear tidal features indicating active gravitational interaction, visible directly in the data. What made the finding significant beyond its sheer spectacle was the measured rate of star formation happening inside this merger. Roughly 250 new solar mass stars forming every single year. For comparison, our own galaxy today produces somewhere between 1 and 3 new stars per year across its entire extent. This ancient 5-way merger was producing stars roughly 100 times faster than our galaxy manages today, concentrated into a single event occurring when the universe was barely 6% of its current age. The lead researcher stated plainly that a merger involving this many galaxies wasn't expected to occur this early under any existing theoretical framework. The chemistry compounded the surprise. Oxygen showed up in this merger's light too, the same signature of multiple completed stellar generations found earlier in that record-breaking oxygen-bearing galaxy at 290 million years. By 800 million years, its presence was somewhat less shocking in absolute terms, but it still confirmed something important. Stars had already formed, lived out complete lifespans measured in millions of years, enriched their surroundings, and contributed their mass to a subsequent generation, all within a period shorter than the time that's elapsed on Earth since the asteroid impact that ended the age of dinosaurs. This observation complicates the idea of what counts as calm and violent on cosmic timescales. In the present-day universe, galaxy mergers still happen, but they're relatively spaced out and infrequent. The overall rate of star formation across the universe peaked roughly 10 billion years ago, an era sometimes called cosmic noon, when merger activity ran roughly 10 times higher than it does today, pushing evidence of extreme merger-driven star formation back to 800 million years, well before that peak, shows that violence wasn't a phase that built up gradually over time. It was present essentially from the moment galaxies existed as distinct structures at all. This distinction matters because it reveals something about our own moment in cosmic history. The relatively quiet current era, the one this telescope operates in, the one our solar system exists in, the one where the approaching collision with our galactic neighbor hasn't started yet, isn't a representative sample of the universe's overall behavior. It's a quiet interval inside a much longer story whose dominant mode has consistently been chaos. The structures that feel fixed and permanent from any human vantage point, galactic disks, stellar populations, planetary systems, are all products of violence that happens to have temporarily subsided. Calm isn't the universe's natural resting state. It's a pause. That character, building structure by destroying smaller structures, assimilating through disruption, organizing through repeated episodes of catastrophic reorganization, is visible across the entire timeline of the universe, from the instant after the beginning right through to the present moment, without interruption. Within the first fraction of a second, the universe underwent an exponential burst of expansion so extreme that regions once in contact were pushed apart faster than light could ever reconnect them again. Temperatures fell from incomprehensible values to merely extreme ones. Protons and neutrons formed out of a hot soup of fundamental particles. Light atomic nuclei assembled within the first few minutes. Hundreds of thousands of years later, electrons finally combined with those nuclei to form the first neutral atoms, releasing the light that still reaches us today as the cosmic microwave background. Then came darkness, a period lasting hundreds of millions of years during which nothing visible existed anywhere. The first stars that finally ended that darkness were unlike anything in today's universe, formed from pure hydrogen and helium, uncontaminated by any heavier elements. They were almost certainly massive, some theorized to have been hundreds of times heavier than a typical modern star, and short-lived, with lifespans measured in millions of years. When they died, some collapsed straight into black holes without ever exploding, swallowing their own mass whole. Others detonated as supernovae far more energetic than anything seen in today's universe, scattering oxygen, carbon, nitrogen, and heavier elements out into the surrounding gas for the first time. The next generation of stars formed from gas already enriched by those deaths. The chemical clock of the universe started ticking with that very first supernova. What this telescope has shown is that the violence of those earliest eras wasn't a brief prelude before things settled down. The observations spanning roughly the first 100 to 700 million years describe a universe where mergers, extreme bursts of star formation, black holes growing far past their theoretical speed limits, and gravitational disruption of forming galaxies were all happening simultaneously and repeatedly, with barely any pause between events for the structures they produced to settle before the next disruption began. The early universe built order through chaos, every episode of destruction setting up the conditions for the next round of construction. Every star in our own galaxy today carries the chemical fingerprints of that ancient violence, written directly into its composition. The oxygen, carbon, iron, and calcium present in every living thing on Earth were forged inside stars that died long before our solar system ever formed, scattered by supernovae into the gas and dust between stars, eventually swept up into the cloud that collapsed to form our own star and the planets orbiting it. Every atom in every complex molecule in every living cell on this planet is, in a very literal sense, the product of stellar violence spread across billions of years of cosmic history. Biology in this framing is chemistry, built out of physics that emerged from catastrophe. The relative stability that makes life possible, the quiet current era, the near-circular orbit of our planet around a middle-aged star, the absence of any nearby supernova in recent geological time, is a temporary condition inside a universe whose default setting is the constant redistribution of matter through gravitational disruption. We exist during an interval of reduced violence, inheriting a planet built from the debris of ancient catastrophes, orbiting a star that will outlive us but not the universe. The violence hasn't ended. It's only paused locally, which brings the story back to those little red dots, the compact black hole-dominated objects introduced earlier as isolated puzzles. Viewed against everything else this telescope has now documented, they look less like anomalies and more like an expected consequence. The several hundred objects cataloged so far show up at distances corresponding to roughly 600 million to 1.3 billion years after the beginning. Compact, red, with black holes ranging from 1 million to 100 million solar masses, accounting for 30% or more of their host galaxy's total stellar mass, compared with a typical present-day ratio of roughly 0.1%. What the broader picture of early cosmic violence suggests is a plausible mechanism behind that relationship. In the early universe, mergers were frequent and intense, and every merger funnels enormous quantities of gas toward the centers of the colliding systems, feeding rapid star formation and rapid black hole growth at the same time. If early mergers really were as extreme as that 5-galaxy collision found at 800 million years, 250 new stars per year, chemical enrichment already well underway, then the conditions needed for runaway black hole growth may not have been rare or exotic at all. They may have simply been the standard experience of a young galaxy in the early universe, not a special case requiring an unusual mechanism, but the predictable outcome of a cosmos running faster, hotter, and more chaotically than any model anticipated. Follow-up spectroscopy in 2025 found that at least some of these objects produce far more ultraviolet light than a pure black hole accretion disk alone would explain, suggesting the central black hole and the surrounding stellar population are both contributing meaningfully to the light being observed. The boundary between black hole light and starlight in these systems may not be as clean as the earlier classification implied. Researchers studying them acknowledge they're still struggling to interpret exactly what they're seeing. That struggle has gotten more specific over time. It hasn't resolved. What these objects seem to represent, in the larger story this telescope is telling, is a universe that built its most extreme structures first. The largest black holes, the most massive galaxies, the most intense mergers, all showing up earlier in cosmic history than any model predicted. If the present-day universe looks calmer, more diffuse, more spread out, it may simply be because the version of the universe we use to calibrate what counts as normal is itself a diminished, cooled-down remnant of something far stranger that came before. Something even stranger sits at the largest scales measurable. Something that doesn't just challenge one parameter of the standard model, but questions an assumption baked into nearly all of them. Einstein's general theory of relativity rests on a foundational premise so basic it's rarely even stated as an assumption, that at sufficiently large scales, the universe is roughly uniform in every direction, with no region fundamentally different from any other. Nearly every major equation in modern cosmology depends on this. Under that assumption, structure should smooth out statistically past a certain size. No coherent object should persist beyond a specific theoretical limit before dissolving into overall uniformity. In 2013, a team spanning several universities detected a statistically significant clustering of gamma-ray bursts across an angular patch of sky that translated into a physical scale at the object's inferred distances, implied a structure roughly 10 billion light-years long and about 7 billion light-years wide. The finding drew attention from specialists but didn't immediately enter mainstream cosmological discussion as a confirmed structure. In 2025, an expanded analysis using a larger catalog of gamma-ray bursts revisited the original detection and confirmed it at even higher statistical significance, and found the structure was even larger than the initial estimate suggested. It spans roughly 10% of the entire diameter of the observable universe. If the assumption of large-scale uniformity is correct, this object is roughly 8 times too large to exist as a single coherent structure. It shouldn't be one connected thing. The matter within it should have been smoothed out by early universe dynamics well before reaching this scale. And nothing in the standard model produces structures this size. It isn't alone either. A different massive structure identified in 2003 spans about 1.4 billion light-years, just above the theoretical uniformity limit. Another identified in 2016 reaches roughly 1 billion light-years. But the 2013 structure sits in an entirely different category. It exceeds the maximum permitted size by such a wide margin that fitting it into the standard framework requires either revising the large-scale uniformity assumption, which would ripple through the entire field, or finding a flaw in the detection method that no subsequent reanalysis has managed to locate. This telescope's own deep survey data reinforces the same conclusion from another angle. The largest observable scales of structure formation simply aren't following the standard predictions. The impossibly massive early galaxies, the improbably early black holes, the 800 million year five-way merger, and this enormous gamma-ray burst trace structure all point the same direction. Something about either the universe's initial conditions or the physical processes governing it since differs meaningfully from the standard description. The largest structure ever detected may be the clearest visible evidence yet that our model has boundaries we simply haven't mapped. And the observable universe itself, everything discussed in this entire story so far, is only the smallest fraction of what likely exists. What this telescope can see is bounded by physics no engineering advance can get around. The observable universe has a finite edge, not because space itself ends there, but because light has only had 13.8 billion years to reach us, and space has been expanding the entire time that light was traveling. When cosmologists describe the observable universe as roughly 93 billion light years across, larger than the age of the universe alone would suggest it's because the regions we're now observing were much closer to us when they emitted the light we're only now receiving, and have since expanded to far greater distances. The edge of the observable universe isn't a wall. It's simply the surface beyond which information hasn't had time to reach us yet. Space, matter, and physics continue past that boundary. They just remain permanently inaccessible to direct observation. Light emitted out there is technically traveling toward us, but the expansion of space between its source and our position is carrying that source away faster than the light can ever close the gap. It will never arrive. So how much larger is the total universe beyond what we can see? The question can only be approached probabilistically, since direct observation is impossible by definition. A 2011 analysis using statistical model averaging across the best available cosmological data, run by researchers at Oxford, Imperial College London, and Johns Hopkins, concluded that the total universe is at minimum around 250 times larger than the observable portion. More recent analyses using updated data have produced estimates ranging up to roughly 400 times larger. And in the extreme case where the universe turns out to be perfectly geometrically flat, which the data marginally favors, the total extent would be infinite. 250 times larger implies a minimum total diameter on the order of 23 trillion light years. If the 93 billion light year observable universe were a single page in a book, the total universe would fill a book at least 250 pages long. And if it's flat and infinite, the pages simply never stop. What this implies is sobering. This telescope, with a mirror gathering nearly 6 times more light than its predecessor and detectors sensitive enough to catch objects 100 times fainter than anything seen before, is still only observing, at absolute minimum, roughly 1/250th of the actual universe. Every impossibly massive early galaxy, every little red dot, every structure that stretches or breaks the assumption of large-scale uniformity, every dark matter filament, every supervoid, every supercluster documented across this entire story exists entirely within a bubble representing only a small slice of the total. Beyond that bubble, physics presumably continues exactly as it does here. Structures presumably exist. Galaxies presumably formed and evolved through all the same violent processes this telescope has documented. The significance here isn't really about scale for its own sake. It's about the limits of what we can ever actually know. Every theoretical framework in cosmology has been built entirely from data gathered inside this one observable bubble. Whether what we can see is representative of the total universe, whether the patterns and anomalies this telescope keeps finding are typical or purely local, is a question that may never be answerable. The universe beyond our horizon isn't going to answer it for us, and that horizon, it turns out, is already shrinking. That boundary isn't fixed in place. Space keeps expanding, and as it does, the line between what's observable and what's permanently out of reach keeps moving outward in a way that excludes more of the cosmos from our view with every passing second. Right now, continuously, more galaxies are crossing what's called the cosmic event horizon, the point beyond which a galaxy's recession speed, driven by dark energy, exceeds the speed of light, meaning its light will never reach us again, no matter how long we wait. The long-term consequence of this ongoing process is more disorienting than almost anything else in this story. Within roughly the next 100 billion years, about 7 times the current age of the universe, every galaxy beyond our own small local cluster will have crossed that horizon for good. Our local cluster itself, held together by mutual gravity strong enough to overcome the local expansion, will remain intact. But everything else, every other galaxy in the observable universe, will simply be gone, and not just faint or hard to detect. The light they emit will never complete the trip. No future instrument, no matter how advanced, will ever detect them again. What this means for any civilization that might exist that far into the future was worked out precisely in a 2008 paper by researchers at Arizona State and Vanderbilt. A civilization arising in that distant era, examining its own sky with the best instruments imaginable, would find only the stars of our own merged local cluster remnant. There would be no detectable cosmic microwave background. It would have stretched by expansion to wavelengths too long for any physical instrument to register. There would be no distant galaxies to measure redshift from, because there would be no detectable galaxies outside their own tiny local remnant. There would be no evidence the universe was ever smaller, hotter, or younger. No expansion to measure at all, no cosmic history legible anywhere in their sky. Applying full scientific rigor to the only data actually available to them, they would very reasonably conclude that the universe consisted of a single, moderately sized stellar system, drifting alone in an infinite static void. The entire multi-century arc of cosmological discovery, from the earliest confirmation that other galaxies even existed through this telescope's own catalog of 500-million-year-old mergers, would be completely unavailable to them and permanently unreconstructible from whatever evidence they'd have left to work with. The implication that follows is very specific. We exist during the only era in the universe's entire history when its full past is actually legible. The cosmic microwave background is still detectable right now. Galaxies from the very earliest eras are still visible right now. The expansion is still measurable, and its history is still recoverable through careful surveys. Nearly 14 billion years of cosmic evolution, from the first quantum fluctuations, through the first stars, through all the violence of the earliest mergers, through the eventual formation of our own solar system, is accessible right now from our current position in time. This narrow window, a few billion years out of a universe that will exist for a minimum of several tens of billions more, is the only interval during which the entire picture is available to any observer anywhere. No civilization arising after this window eventually closes will have the evidence necessary to ever reconstruct what came before. What we currently know is something that will not remain knowable forever. This telescope arrived right at the beginning of the last era, in which reading the universe's complete history is even physically possible. And what it's found in reading that history points toward three distinct possible endings, each of them absolute and total, none of them currently distinguishable from the other two. Three futures currently exist side by side in the state of cosmological knowledge, and none of them can be ruled out by any measurement currently in hand. They aren't fringe speculations sitting at the edge of the field. They're the three principal outcomes the actual data permits right now, each supported by a different subset of the evidence, each ending in a totality so complete that the word ending almost undersells it. The first is heat death, sometimes called the Big Freeze, the outcome that held consensus status for roughly 2 decades after accelerating expansion was first discovered. Under this scenario, dark energy stays constant or weakens too slowly to matter much. The universe just keeps expanding forever. Every galaxy beyond our own local cluster disappears beyond the cosmic horizon within about 100 billion years. Over the following 100 trillion years, the remaining stars burn through their fuel, cool, and go dark. Our own galactic remnant becomes a slowly cooling cloud of stellar corpses, radiating away their last heat across unimaginable timescales. If certain theoretical extensions to particle physics are correct, even protons eventually decay, over timescales measured in numbers approaching 10 to the 33rd power years. Black holes, more stable against that kind of decay, eventually evaporate too, through an extremely slow quantum process, over timescales approaching 10 to the 100th power years. After the very last black hole finally evaporates, only the faintest possible trace of thermal energy remains, spread across a volume of space so vast that the very concept of temperature stops meaning anything. Maximum entropy. No further change is even possible. This state simply persists because at that point, forever is genuinely what's left. The second is the Big Rip, the outcome permitted by that phantom energy behavior the newer survey data suggested the universe passed through in its own past. If dark energy's behavior ever returns to that phantom regime, the repulsive force grows without any limit as space keeps expanding. Running the critical timeline backward from the final moment, roughly 2 billion years before the end, galaxy clusters lose their gravitational cohesion entirely. 60 million years before the end, our own galactic remnant is destroyed. 3 months before the end, our planetary system is torn apart as the expanding repulsion overwhelms our star's gravity. 30 minutes before the end, Earth itself is pulled apart. In the final fraction of a second, individual atoms are torn apart as the force finally reaches down to the scale of nuclear bonds. This version of the universe doesn't cool quietly into silence. It accelerates through the destruction of structure, then chemistry, then physics itself, until literally nothing bound together survives anywhere. The third is the Big Crunch, revived by that 2025 analysis suggesting the cosmological constant might be effectively negative at the deepest level, meaning gravity eventually wins its long competition against expansion. In this version, expansion decelerates, halts, and reverses over roughly the next 11 billion years. The sky, which stays dark for hundreds of billions of years under the other two scenarios, instead grows brighter as the shrinking volume of the universe concentrates the cosmic microwave background back into visible wavelengths. Every structure gravity assembled across the entire history of expansion gets compressed back together. In the final stages, everything dissolves into a fireball of shrinking scale, collapsing back into the same kind of singularity the Big Bang itself emerged from. Each of these three endings is absolute. None leaves any remnant behind. None offers any physical mechanism by which information about what came before could possibly survive into whatever, if anything, comes next. The universe will end. The only real uncertainty left is which specific form that ending takes. And that uncertainty isn't some small gap between three nearly identical outcomes. It's a genuine three-way split between a cold, eternal fade, a violent accelerating dismemberment, and a total crushing collapse, governed entirely by the behavior of a force that makes up 68% of everything that exists, and that we currently cannot characterize precisely enough to choose between any of the three. This telescope began its science operations in the middle of 2022. By early 2026, roughly 3.5 years into its primary mission, it had already forced revisions to the standard model of cosmic evolution, confirmed a genuine, unresolved crisis in the measured expansion rate of the universe, detected chemical signatures inside the oldest confirmed galaxy demanding multiple complete stellar generations had already lived and died before the model said the first stars should even exist, and cataloged an entire population of black holes so massive and so early that no accepted physical mechanism currently explains them. It showed us 5 galaxies merging together at 800 million years old. A single star fleeing our galaxy's center at 6 million kilometers an hour. Cosmic structures that exceed the theoretical maximum permitted size by a factor of 8. None of these results are unsettling because of their sheer spectacle. They're unsettling for something more precise. The specific discomfort of realizing that the exact framework used to understand the universe, a framework that had passed every observational test thrown at it for 4 decades, was systematically wrong in ways we haven't fully mapped out yet. Every measurement that should have simply confirmed the model instead deepened the crisis. Every anomaly that early observations flagged as probably resolvable with better data became less resolvable as the data actually improved. This telescope didn't teach us the universe is large. We already knew that. Humans have known the rough distances to other galaxies for about a century now. That knowledge has been fully absorbed into textbooks, planetarium shows, and every introductory astronomy course taught for the past 80 years. Familiarity with scale isn't what produces unease here. What this telescope actually added was uncertainty at the very foundation. The disagreement over the expansion rate isn't a measurement of how big the universe is. It's a measurement of how well we actually understand it. And the answer, confirmed by the most precise instrument ever built for the job, is that we don't understand it well enough for our 2 best measurements to both be correct at the same time. Dark energy makes up 68% of the total energy in the universe, may be actively changing, and we still don't know what it fundamentally is. The structures visible in the early universe show up at scales and densities the standard model simply doesn't produce. The basic assumption that the universe looks roughly the same everywhere on large enough scales runs headlong into a structure 10 billion light-years across that appears to violate it by a factor of 8. The eventual fate of the universe sits genuinely undetermined between three separate endings, each of which terminates absolutely everything. The unease here isn't that the universe is large enough to make us feel small. That's an old, familiar feeling. It's that the universe is strange enough to make our entire understanding of it feel provisional. We exist on a planet circling a middle-aged star, tucked into the outskirts of a fairly ordinary galaxy, itself a minor member of a supercluster slowly flowing toward an attractor we can't even fully see directly. Embedded inside a void roughly 6 times larger than the most extreme void previously known to exist, inside a universe whose expansion rate we can't reconcile, whose dominant energy component we can't identify, whose earliest history doesn't match our best models, and whose ultimate fate remains genuinely undecided between 3 separate total endings. Our species has existed for perhaps 300,000 years. We've had instruments capable of measuring any of this for maybe a century. We've had this specific telescope capable of reading the oldest light in existence for a little over 3 years. The window during which the universe's full history remains legible closes in roughly 100 billion years, which sounds distant. Until you remember, the universe has already existed for nearly 14 billion years and is expected to persist for a minimum of 30 billion more. We arrived late in the only era when this evidence was still available to gather, built the precise instrument capable of reading it just before that window began narrowing, and discovered, once we finally looked, that almost everything we thought we understood needed revising. This telescope didn't reveal that the universe is terrifying because of how big it is. It revealed something closer to the opposite. That after everything we've learned, we still understand shockingly little of it. What we can see in this brief window where the universe is still comprehensible at all is enough to know that the questions we still can't answer are exactly the ones that matter most, and that the very instrument reading them won't remain operational nearly long enough to resolve them. The universe will keep operating under rules we haven't fully identified, at scales we can't fully observe, moving toward an ending we can't yet determine. And we're here, watching, for only a fraction of the time it will take for any of it to finally play out.